Hello everyone. Now we're going to apply a combination of mass, energy, and entropy balance equations for a problem looking at heat exchanger design, and it's very basic. So the goal of the problem is to determine the temperature distribution, the length of exchanger needed, and the entropy generation. And we have two options. This is a problem that's based off of a problem in Stanley Sandler's book that looks at heat exchangers. The first of the two we're going to look at is what's called a co-current heat exchanger, where the temperature of the inlet stream that's being cooled and the temperature of the inlet stream that is the coolant enter on the same side. And they exchange energy by being in thermal contact with each other, even though there is no mass flow between the two streams. The mass is separated. And then the goal of this is to go from a temperature of 35 degrees centigrade to 15 degrees centigrade. And then this is the cooling stream. So we have two different temperatures, temperature 1 and temperature 2. And we're going to have to do combined energy mass balances to account for both how these are changing in length, but also how they are impacting each other by the contact that they have. Following the first example, we'll revisit it with a countercurrent example. More specifically, we're going to consider the heat transfer as happening per unit length of the heat exchanger, where there's contact between the streams, and the heat transfer is occurring through a heat transfer coefficient and the temperature difference between the two streams that serves as the driving force for this transfer. So how do we approach a problem like this? We haven't yet done a problem that varies over space like this one. The way that we do this, and this is something that's very commonly done in fluids and transport courses, is to consider a small element here that has a unit width of delta L, a small interval delta L, that is extracted from the picture above. Then so the interval goes from L plus delta L, and you look at what's happening inside of this small control volume. So for the mass balance equation, we would have the mass at some time in the future, time t plus delta t, inside of that, minus the mass at some time point in the past t, is going to be equal to the mass flow in that's coming in at position L, and it's got a dot there to denote that it's a flow rate, so times delta t minus the mass that's flowing out at position L plus delta L times the time interval over which that's happening. This way, the total mass in the system will be just equal to the difference in the flow rates and the time intervals over which those flow rates are happening. In this problem, we're going to consider steady state operation. And so then 0 is going to be equal to m in at L times delta t minus m out at L plus delta L times delta t, but delta t is some non-zero small number you can divide through by it, and the mass balance gives us is a trivial balance, and that is that the mass in is equal to the mass flow out, which we're going to just simply eventually we'll just substitute in and define it as the mass flow for stream 1. We have to be careful with keeping mass flows in stream 1 and 2 separate, and depending on how we design our control volumes for the two separate streams, we might have to account for a minus sign, and in fact that's what we're going to do a little bit later. So that's what our mass balance gives us. Check. And every time you do these problems, you do the mass balance, the energy balance, and the entropy balance. So let's move on to the energy balance now. We have to do it with a similar new derivation for this control volume. So let's just call it the energy, or you can use U for internal energy at time t plus delta t minus the energy, energy at some time t is equal to the flows of energy in and out of the system. But we know that this whole thing is operating at steady state, so we don't expect any energy accumulation. So let's just use that right from the beginning to make our life a little bit easier with the derivation. So we're going to start with 0. Now what's on the right-hand side of the energy balance equation? If you look at the previous lectures, you see the entire energy balance equation. We have to account for the streams. So we're going to have the stream here, M1, that's flowing in at the left-hand side boundary, times what the stream is bringing with it, which is the enthalpy at position L, and it's doing so over time interval delta T. And this is that's leaving with enthalpy L plus delta L times the overall time interval over which it's happening. And this is balanced plus the heat transfer that's occurring per unit length times the length of that interval times the time interval over which it's happening. So again, we're able to just eliminate the delta t's by dividing through by them because it's a non-zero small number, and we're left with a simpler equation. 0 equals m1 times hl minus hl plus delta L. Okay, there's a mass flow rate, be careful with that, plus Q dot times delta L. Move this to the other side, and we're going to have M1 times HL plus delta L minus H at L. I got to get the underbars there to make sure that we're doing it per unit mass. And this is going to be equal to a plus Q dot delta L on the other side of the balance equation. Now, if you recall that we can replace, well, first thing we're going to do is we're going to invoke the eagles. Okay, the eagles, and take it to the limit. One more time. It's well, it's a song by the Eagles. You judge whether or not you like it or not. I think once you've taken it to the limit over and over and over, it just becomes no longer a limit. It's just natural. M1 dot. And then we can replace the enthalpy as well. So let's just go through it. We'll have dH dL on this side now that we're taking it to the limit of delta L goes to 0 equals Q dot. But then we can replace H with our lovely relationship for substituting for H in terms of CP. And so then we can replace this term, dH dL, with M1 CP1 d temperature 1 dL, because the reference temperature doesn't change in L, so it disappears. And this is now going to be equal to Q dot, which is going to be equal to the kappa, the heat transfer coefficient, T2 minus T1. So now let's rewrite this down in simpler form. M1 CP1 dt1 d unit length is equal to K times T2 minus T1. Now we do the same balance for stream 2, and you end up with M1 equals M2 because they're flowing in the same direction, CP2 dt2 dL, but this is the opposite heat transfer. So this is going to be minus K times T2 minus T1. Because what you lose from one stream, you enter into the other. And so these two terms have to be in the opposite. One thing you'll notice that's pretty clever about this setup is that we have these two terms here that when you sum them together, they will cancel each other out. So if we add equation 1 to equation 2, we end up with, and then if we have M1 dot equals M2 dot for equal flow rates, we're going to have this final differential equation, dt1 plus t2 dl equals 0, because these two terms cancel out right here. You can divide through. We also require that the CP1 equals CP2, so the same heat capacity in the two materials, and you end up with this differential equation. This is a trivial differential equation, T1 plus T2. Then the only solution of this is going to be some integration constant. This is just an integration constant. Okay, so great. What can we do now? Well, now, instead of two coupled equations, we can simply sub in this relationship and eliminate a single variable, a single dependent variable. This allows us to solve it. Whereas before, we'd have to solve this as a coupled system because we have T1 and T2, with T1 and T2 both entering into each other's equation. But now with the substitution, our life's a lot easier. So here's what we can do. We say now dt1 over dl is equal to k over m dot cp. We just multiplied through by mcp times t2 minus t1. But following the substitution, this is equal to k over m dot cp times c minus 2 times t1. Now, all we have to do is integrate. We have a separable differential equation in T1. So let's do this calculation. We're going to integrate this thing for stream 1 from T1, the initial temperature, to T1 final temperature, dt1 divided by C minus 2T1, because we just divide through by this term right here. And this has to equal the trivial integral of k over mcp dl over the length of the heat exchanger. So we have to do reverse chain rule. The integral of this is minus 1/2 of the natural log of c minus 2 times t1, evaluated at t1 initial and t1 final, and this equals k times L over mcp. So with T1 initial and T1 final, we're able to use the law of logs, and this now equals ln. Move the minus 1/2, move the 2 to the other side, use the law of logs to rearrange this. We're going to end up with c of minus 2 T1I on top, and then C minus 2 T1F in the denominator of that logarithm, calculated out, equals now 2 times K times L over M dot CP. Okay. That is the solution for the overall temperature distribution in this. One thing that was interesting is that in this problem statement, this quantity here, K over MCP, has units of length. And this can be defined as some L0 is equal to MCP divided by K. So L0, this is some characteristic length that depends on the properties of your material, specifically the properties of the heat transfer and the heat capacity. So we can reframe this whole thing in terms of these units of length. So if we can keep the 2 in there as well, we'll just bundle the 2 into our L0 calculation. So we'll keep the 2K with it. So this is our definition for the characteristic length in the heat exchanger. So if we use L0, our definition here, because the units work out, m dot Cp over 2k, we can do a few more calculations. Starting with, we have at length L, we know that for this temperature to drop, we have to go from T1I equals 35 degrees C to a T1F equals 15 degrees C. So we can plug these values in for I and F in this. And we have to recall where C equals T1 plus T2. This also is consistent at the ends. So this could be equal to T1 initial plus T2 initial. Or the same thing would be measured at T1 final plus T2 final. It just happens when you add up those numbers together, you end up with 20 degrees C. So our constant for this first problem is 20 degrees C. So substituting this in for C, this value in for T1I, this value in for T1F, we will have now for our overall equation at the length L, the natural log of 20 minus 2 times 35, all divided by 20 minus 2 times 15, and this equals 2k over MCP times L, which we define as L over L0. When you plug this into the natural log and calculate it, you get this as being the natural log of 5, and the natural log of 5 is approximately 1.61. So then we can calculate the length of our heat exchanger based on the material properties for this whole thing to work is 1.61 times this length L0 definition that we have defined from the properties of the material. So that calculates the temperatures, the equations for temperature, the length you need. If you want to expand this, we can go back to our equation, C minus 2 times T1 times L divided by C minus 2 T1I. I take the log of, this is the log of both sides, equals minus L over L0. Okay. That looks like L over 10. This is equal to, let's just leave it as 2K over MCP. So, take the exponential of both sides of this, okay, rearrange, and you end up with T1 as a function of L equals 25 e to the minus L divided by L0 plus 10. This we'll call equation 4. And then simply using the relationship that T1 plus T2 equals C, you can calculate T2 at any position L. In this heat exchanger equals 10 minus 25 E minus L over L0, equation 5.